Hello again. This is Math 2231 remote delivery for April 14th, 2020. This is part 2 and we're introducing the definite integral. Make sure you use these kind of tools to we're going to define the definite integral. So given a function f of x that is continuous on the closed interval a, b, we divide the interval into n subintervals of equal width. We're calling that delta x. And from each interval we'll choose a point, and that will be xi star. Then the definite integral of f of x from a to b is, and the way we read this is the definite integral from a to b of f of x dx is equal to the limit as n goes to infinity of the summation as I goes from 1 to n of f evaluated at x sub I star times delta x. Now, this definite integral is exactly the limit and summation that we use to talk about the net area between a function and the x-axis. And that's going to be a useful geometric characterization of the definite integral. Note also that the notation for the definite integral is very similar to the notation for an indefinite integral. The only thing is we have definite limits of integration. That will become clear why we use this notation later. We also call the number a at the bottom is called the lower limit of the integral, and the number at b is called the upper limit. Despite the fact that a and b were given as the interval, the lower limit does not necessarily need to be smaller than the upper limit. We'll see that later today. And collectively, we'll call the interval from a to b the interval of integration. Okay, so now here's a problem I would like for you to do. Use the definition of the definite integral to compute the following function. Now notice that this is a function that we have looked at before in the previous section. So we want to compute the definite integral from 0 to 2 of x squared plus 1 dx. Pause now to test your understanding. Let's see how you did. Well, first, we can't use the definition unless we determine which point in the interval to use. And to make life easier, we're going to use the right endpoints. If the integral exists, it exists independent of what point you choose. So from the previous section, we know that what we can do is we can set delta x to be equal to 2 minus 0 over n, or 2 over n. So when we slice it into the interval from 0 to 2 into our pieces, we get subintervals look like this. And as you can see, the right endpoint of the ith subinterval is going to be 2I over n. So now what we're going to do is evaluate the sum before we take the limit. So we're going to look at this expression, and we're going to substitute for all our xi stars 2I over n, and delta x is always 2 over n. So we get this expression. You see, when we place 2I over n into x squared plus 1, we get this plus this. Then we're going to do algebra, distribute this 2 over n, and we'll get this expression. And that's what we're going to need to evaluate. And we're going to be using our properties of sums that were in part 1 to evaluate these. Okay, so we're going to do it term by term. And we're going to be able to pull out of this sum. And by the way, you see 8 is a constant, but also we're summing on I. So you see n is also a constant. So I can pull 8 over n cubed out of here because it doesn't depend on I. So I have left this expression, the summation I equal 1 to n of I squared. Over here I can pull out the 1 over n, and I have the summation of 2 from I equal 1 to n. So now I have 8 over n cubed, which is just this, but we have a formula that we have memorized for this sum, and it is this expression. So the summation of I squared as I goes from 1 to n is known to be this. And we also learned that the summation of a constant, in this case 2, from I equal 1 to n is just c times n, or in this case 2 times n. We again do algebra and simplify, getting this expression, and then we get the common denominator and we simplify it to be this expression. There's quite a bit of algebra that you should verify is correct here. You will be being asked to do this kind of algebra. So now the only thing that remains is for us to take the limit of the expression. So we're taking the limit as n goes to infinity of the sum that we calculated. Now as you look at this, the degree of the numerator is n squared, or 2 I guess, and the degree of the denominator is n squared, or 2. So the answer to this is just the ratio of the leading coefficients. It is 14 over 3. See you in part, this is the end of part 2. See you in part 3.